Okay, I think we can start. It's 5 o'clock in Belgium. So hello everybody and welcome to today's MCLS symposium. The topic of today is insights into predictors and correlates of proportional reasoning. Our symposium wants to add to the current research by not merely looking at proportional reasoning as such, but by also relating it to other research domains. The research domains we will discuss today have mainly developed separately, but constitute important predictors and correlates of proportional reasoning. And therefore, we think it is important to investigate them in parallel. I will give the first presentation today. I am Elien Vanluydt, a PhD student from the KU Leuven in Belgium, and I will talk about the association between patterning and proportional reasoning. The second presentation will be given by Professor Jake McMullen from the University of Turku in Finland, and he will talk about the relation between spontaneous focusing on relations and word problem solving in the domain of proportionality. The third presentation will be given by Professor Wim van Dooren, also from the KU Leuven in Belgium, and he will talk about inappropriate additive reasoning in the domains of proportionality, probability, and fractions. I'm also very pleased that Professor Matthew Inglis from the University of Loughborough agreed to be our discussant today. I think that will be very interesting. And if everything goes well, we will still have 10 minutes left for some questions. So, let's start. As I said, I am Elien Vanluydt, a PhD student at the KU Leuven, and my PhD project is part of a large longitudinal project called the Wiz & Co project, and it investigates the development and stimulation of core mathematical competencies in early childhood. Today, I will focus on a small part of this project in which we investigated the association between patterning and proportional reasoning in early childhood. So first, what is proportional reasoning? Proportional reasoning is reasoning about a relationship between ratios. Some also say reasoning about relations between relations, but most simply said, it's the ability to compare two things using multiplicative reasoning and then apply this to a new situation. We very frequently use proportional reasoning in daily life situations. A typical example are recipes or exchanging currencies. Proportional reasoning is also considered one of the biggest math ideas children have to develop in elementary school. It is also considered a critical concept for success in secondary math because it is essential for learning other advanced mathematical topics such as algebra, geometry, statistics, and probability. But despite its importance, the concept of proportion is considered hard to apprehend for children. In Flanders, proportional reasoning is introduced in the 4th year of elementary school, but at the end of elementary school, only one third of the children does not reach the required learning outcomes regarding proportional reasoning. And Resnick and Singer said it very beautiful. They consider it one of the stumbling blocks of the middle school curriculum. So given that crucial role of proportional reasoning in mathematical development and the difficulties children and even adults encounter in acquiring proportional reasoning competency, more insight into the early development and potential predictors of proportional reasoning is required. So far, empirical research has mainly focused on numerical and general cognitive abilities as predictors of proportional reasoning in adolescents and adults. But recently, this narrow focus on numerical abilities has been questioned. First, because mathematics is much more than only numerical abilities. It has been described as the science of patterns and relationships. Second, a meta-analysis has shown that children's numerical abilities explain hardly 6% of the individual differences in general mathematics achievement, and this suggests that other variables might contribute more substantially. And third, the early stimulation of children's basic numerical abilities and intervention studies yielded mixed findings. Today, I will focus on patterning as a potential predictor of proportional reasoning. because several theoretical and empirical reasons have been put forward to suggest an association between both. Theoretically, there are similar mental activities involved in reasoning about patterns and reasoning about proportion. An important step in the transition from patterns to algebra is to consider the association between the two quantities and to describe this association in general terms as a numerical relation. If this association is multiplicative, as is the case in repeating patterns and specific growing patterns, the description of the association between two variables requires similar insights and understandings as in the description of proportions. Empirically, patterns have also been suggested to be valuable to support multiplicative reasoning, which is an important insight into proportional reasoning. However, the question still remains whether both abilities are related at a younger age. To address this gap, the current study explored if patterning in the second grade of kindergarten is related to proportional reasoning 1.5 years later, when children are in the first year of elementary school. For our patterning measure, we included repeating and growing patterns because both are assumed to be relevant for proportional reasoning. And for proportional reasoning, we included a task with only discrete quantities, but also a task with a discrete and a continuous quantities, because the nature of the quantities might impact children's performance on proportional reasoning tasks. Two research questions were formulated. The first, in which way is patterning in 4 to 5-year-olds associated with proportional reasoning 1.5 years later? And the second, does this association hold after controlling for sex, age, cognitive, and numerical abilities? We collected data from 346 children from 17 schools. Data on patterning abilities were collected in the second grade of kindergarten. Data on proportional reasoning abilities were collected in the first grade of elementary school. And numerical and cognitive abilities were used as control variables and were collected in the second and third grade of kindergarten. Then onto our patterning measure. We administered 2 18-item patterning tasks, one for repeating patterns and one for growing patterns. Each covered 3 activities, namely extending, generalizing, and identifying. In the extending activity, we asked the children which symbol comes next, and they had to choose out of 4 symbols. In the generalizing activity, we asked the children to recreate the pattern with other materials. And in the identifying activity, we asked the children to copy the pattern from memory. So in total, children had to make 36 items assessing their patterning abilities. Then the proportional reasoning measure. We developed a fair sharing missing value proportional reasoning task to assess these young children's proportional reasoning abilities. 8 items of this task assess proportional reasoning with 2 discrete quantities, and the other 8 items assess proportional reasoning with a discrete and a continuous quantity. In the first 8 items, children were given the following instructions. All puppets are equally hungry. If I give 4 grapes to these puppets, how many grapes do you have to give to these puppets for it to be fair? Children were then instructed to give grapes to the puppets on the right side. They gave the correct answer when they gave 2 grapes to each child on the right side, or 12 grapes in total. Mathematically, that meant that they had to make sure that the ratio between the puppets and the grapes on the left was equal to the ratio between the puppets and the grapes on the right. The items for the task, the items with discrete and a continuous quantity were very similar, but here the grapes were replaced by chocolate bars, a continuous quantity. Several other data was collected and used as control variables. 2 child characteristics, sex and age. a battery testing several numerical abilities such as counting, number comparison, number order, number identification, and basic arithmetic. And several cognitive abilities were assessed, verbal and spatial working memory, spatial abilities, and language. Then on to the results. On average, children scored better on the repeating patterning task as compared to the growing patterning task. And we observed large individual differences between children. For the proportional reasoning task, children scored better on the proportional reasoning task with two discrete quantities as compared to the proportional reasoning task with a discrete and a continuous quantity. And again, we observed a lot of individual differences. Then the correlations. We found medium positive correlations between both early patterning scores and both early proportional reasoning scores. But then when we looked at the partial correlations controlling for child characteristics, numerical abilities, and cognitive abilities, only two correlations remained significant. And that was the correlation between repeating patterns and proportional reasoning with discrete quantities, and the correlation between growing patterns and proportional reasoning with a discrete and a continuous quantity. A hierarchical regression analysis confirmed this pattern when only repeating patterns and growing patterns were in the model as predictors. Both were significant predictors for proportional reasoning with two discrete quantities, but when our control variables were added, only repeating patterns remained a significant predictor together with spatial abilities and language. For proportional reasoning with a discrete and a continuous quantity, again, both patterning types were significant predictors when they were the only in the model. But then when we added the control variables, only the growing patterns remained a significant predictor together with language. So to conclude, this study was the first to explore the association between emergent patterning and proportional reasoning in early childhood. Findings showed that patterning is a unique predictor for emergent proportional reasoning ability over and above sex, general cognitive, and numerical abilities. However, the association between pattern types and the nature of the quantities in proportional reasoning is differential. The findings in this study should suggest that each pattern type is related to a different aspect of proportional reasoning. Future longitudinal studies focusing on strategy use and intervention studies are needed in order to further investigate these associations and to address their educational implications. If you want more information about this study, it has been recently published in Educational Studies in Mathematics. And then I would like to thank you for your attention. If there are any short questions, they can be asked now while we switch speakers. So Jake, you can put up your presentation now.
Are there any questions for Elien before I start?
Okay, then the floor is yours, Jake.
Okay, great. Well, thank you for that. It was an excellent first talk, and I think it's also helpful to, kind of not necessarily. Andy had a question maybe before I start.
That can be addressed in the chat. It was just, the question is, do we think that there's a causal relation where patterning knowledge or patterning abilities might support the development of proportional reasoning in later years? That is, do we think that proportional reasoning is just kind of an extension of patterning in a different way of thinking?
You're muted, Andy.
Yeah, sorry, I was still muted. So there have been some studies that use patterning in intervention studies in older children to introduce multiplicative thinking. But I don't think we can say anything about a causal relationship in our study. I think intervention studies should figure out if there is a causal relation between both. But if you do a rational task analysis of both activities, I think that patterns might be useful to introduce children to proportional reasoning, but I don't think that our study can already make hard conclusions on that part. I hope that answers your question.
Yeah, definitely answers my question and gives us more to think about. Thank you.
Nice. Okay. Well, so I guess I'll go ahead and get started. Yeah, again, thank you, Elien, for getting us started and also introducing the topic. So I don't have to spend as much time on what proportional reasoning is or why it might matter. My talk is going to be a study that we conducted together with Dina de Graan from the University of Leuven, and we're looking at proportional reasoning and the use and overuse in word problems, and how that relates to students' spontaneous focusing on multiplicative relations. So this is a correlational study that we conducted with 7th graders from the US, so they're about 13, 14 years old. Yeah, and so to get started, first to talk about what we mean by spontaneous focusing on quantitative relations, I'll first introduce this idea of spontaneous mathematical focusing tendencies, which is a line of research that's been going on for about 20 years now, examining how students use mathematical thinking and reasoning and notice mathematical aspects of situations that are not explicitly mathematical. So it can be everyday life. Obviously, this is often measured through tasks which are kind of contrived, but meant to be designed in a way that sort of the math is there, but it's not explicitly pointed out to the students. So, and the idea is that those students who pay more attention to mathematics in their everyday environments have more opportunities to practice their existing mathematical skills. They get this, what we refer to as self-initiated practice. So in order to see the math around you, you need to first focus on it. In a lot of instances, there's not an adult or someone else to point it out to you. And this extra practice that they gain outside of sort of formal or explicit mathematical situations leads to also better performance in formal mathematical skills. Quite recently, we had a special issue on spontaneous mathematical focusing tendencies come out in Mathematical Thinking and Learning. And you can find kind of an overview of the field at the moment, at least, in our introduction text with Leuven Verschaffel and Minna Hanula-Sormanen. Leuven and his colleagues have also written a recent review, as have me and Minna. So, you know, kind of if you're interested in digging into this, there's a budding field developing. And in a happy coincidence, the discussant for today, also Matthew, wrote a commentary for that special issue as well, examining some of the sort of open questions, for instance, about causality. Yeah, so examples of spontaneous mathematical focusing tendencies that have been looked at. The first one, the main one, the heart of the field is this idea of spontaneous focusing on numerosity, so sets of exact numbers that exist. In this case, for instance, there's a dinosaur that happens to have 6 spikes on it, and children had to recreate that. My work has extended this from just exact numbers to the relation between 2 or more quantities. Most of the time, this has been multiplicative quantities, and that's what we'll be talking about today. Multiplicative relations, excuse me. So that's spontaneous focusing on quantitative relations, or SFOR. And SFOR tendency is defined as a tendency to defined as the tendency to spontaneously focus attention on quantitative relations and use these relations in non-explicitly mathematical situations. So basically what I said. It's important to note that this spontaneous does not mean sort of the spontaneous development of some sort of skill, but it's a spontaneous use in a particular situation. That's what we mean by spontaneous or unguided. We found that SFOR tendency uniquely predicts mathematical development after controlling for a myriad of other variables, domain-specific and domain-general. So for instance, it predicts the development of rational number knowledge in late primary school students. And as well, there's a iterative relation between SFOR tendency and rational number knowledge in similar time points. So SFOR tendency predicts later rational number knowledge, which predicts SFOR tendency, which predicts later rational number knowledge. And that this also, SFOR tendency is predictive of algebra knowledge as well. So we can see that it's kind of related to different aspects of mathematical development. But one area which we thought would be probably relevant for examining if SFOR tendency might be related is proportional reasoning, and in particular we wanted to examine word problem solving. So as Elien said, proportional reasoning is obviously important for everyday life. There's a lot of activities in everyday life: cooking, calculating rates, thinking about the ratios between different objects. So proportional reasoning is important for everyday life. It's also important in the math classroom. It's, again, sort of not only a capstone of the early years, but also foundational for later learning in algebra and other topics. But of course, students have a lot of difficulties with it. And one particular difficulty that students have is what could be described as the overuse of multiplicative or proportional thinking. So using proportional reasoning in situations that are not appropriate. So for instance, in the situations that's additive, for instance, in the example of, sorry, these are backwards, but so for instance, thinking about word problems, in some instances, for instance, this word problem, the key thing here is that Tom jumps at a different rate than Erica, and therefore this would be a proportional relation. So when Tom has jumped 4 times and Erica 20, then Tom jumps 12 times, how much does Erica jump? Then you need to think about the proportion, the multiplicative relation between these two jumpers. However, in this instance, where Peter and Linus are reading books and they both read at the same speed, then this is going to be an additive relation. And what has been found is that some students tend to over-apply sort of proportional thinking in these additive situations and vice versa. So this is one of the difficulties that students face in thinking proportionally. And of course, in both instances with SFOR and these word problems, the idea is that there's a connection between sort of the real world mathematical thinking and the mathematics classroom, and also as well thinking about how these relations exist in these situations. And so we expected potentially that there would potentially be a relation between SFOR tendency and proportional reasoning in these contexts. So that's exactly what we looked at. So the first research we had in this study was whether the pattern of proportional versus additive problem solving were similar in middle schoolers or different in middle schoolers than in younger children. So this is one of the first studies that looked at it in older students after they've kind of completed a lot of their instruction that is sort of explicitly tied to this proportional reasoning, so fractions and percentages and other kind of, well, proportional topics in the math classroom. And then the second question is whether or not there's a relation between SFOR tendency and proportional and additive word problem solving. So this study was conducted with, like I said, 7th grade students. There's 150 of them about, a little more female than male. And again, these were 7th graders in the US, so they're about 13 years old. We gave them 4 tasks that were developed in previous studies, and these could be described as picture description tasks. Yeah, so the first one on the left is what we refer to as the teleportation task.
Sorry, I hope you can hear me still. Yeah, I guess so. At least the subtitles can. Yeah, so yeah, students are asked to describe in as many ways as possible. On the left, are you okay now? Laughing or crying? Sorry. Yeah, if on the left there's the teleportation task, and they're asked to describe how the objects have changed. As you can see, they've all been changed by a multiplicative relation, but obviously there's other things that have been changed, and we find that students describe these other changes, and for instance, just exact numbers that they're worth 3 and then they're 9. And then there's some students that use what we call exact multiplicative answers, where they say use an exact multiplicative relation in describing them. For instance, in this case, there's 3 times as much. And then a same construction for what we call the lunch task, where these 2 meals, and they have to describe how they're different. Along with these spontaneous versions of the task, where we don't give them any guidance to the mathematical aspects, and we think that any exact multiplicative answer would be described as spontaneous, then we give them what we call guided versions, where we ask them to describe explicitly these multiplicative relations in order to be able to control for the skill and the ability to use and describe the multiplicative relations embedded in the tasks, because it's important to distinguish between the spontaneous focusing and the actual skill needed, and those things that there should still be individual differences in spontaneous focusing after controlling for the ability to think about the multiplicative relations. As well, we give them these proportional and additive word problems. They're from Van Doorn and colleagues. So there were 4 that we used in this study, 2 proportional and 2 additive. And for each type of task, there was one task that included an integer ratio in there, because it's been found that these the ratios embedded in the tasks can also influence how students respond to the task. So when there's an integer ratio, they're more likely to respond proportionally than when there's a non-integer ratio. And that's exactly what was found. So the results from this study show that with older children, there's similar types of responses, that some students, that some use additive reasoning on proportional tasks and proportional reasoning on additive tasks, in this sense of using inappropriately these different types of relations. And that students are sensitive to number features. So for instance, they use more additive reasoning on non-integer tasks and use more proportional reasoning on integer tasks, no matter the actual relation that's being described in the word problem. And just on a variable-centered approach, we see that there is a relation between SFOR tendency and word problem solving. So there's a positive relation between proportional responses and SFOR tendency, and SFOR is negatively related to additive responses, albeit quite small. But then once we control for guided focusing, we see that there is still a relation for proportional responses, yet this is quite small again. So it's only some fairly minor relation, and there's no relation with additive responses. We also found that if we categorize students based on their responses, and this is something that's sort of replicating what was previously done by, for instance, them and colleagues, we find that there's similar patterns as in younger students. There's few students who perform all of the answers in a correct manner. They use the right kind of reasoning on each task, and that there are several erroneous profiles, that some students basically only use additive, some basically only use proportional, and many students are what could be described as number sensitive, so that they're changing their approach based on the integers or the ratios of the relations in the task, whether they're integer and non-integer. And what we found then was, for these groups, we saw that there were differences in the number of SFOR responses by this problem-solving groups. So in particular, the proportional students who overused proportional reasoning, so they had at least 3 of the responses were proportional, and they also had the highest number of SFOR responses in comparison to additive, number sensitive, and other groups, though they didn't differ from the groups of students who got all of the answers correct. And so but also surprisingly, I mean, you can see that at least the students who got all of the answers correct didn't outperform any of the other groups or underperform. So in conclusion, we do see that middle school students, not middle schools, but students still overuse proportional and additive reasoning. and that they are still influenced by numerical ratio. And I think this is in line with previous research that shows, of course, that many students kind of take a surface level approach to solving math problems, and that they're influenced by inputs. For instance, in this case, I imagine if we looked at the textbooks, we would find that most proportional tasks are use integer ratios. Maybe Wim has an idea about that. But of course, this isn't all students, as for instance, David Braithwaite and colleagues found that there are these individual differences there. There was actually only a very minor relation between sport tendency and word problem solving, and it wasn't related to necessarily the correct answers, but actually more towards the use and overuse of proportional reasoning. I don't think I have time for my limitations, but obviously there's plenty. But yeah, thanks for your time.
Thank you, Jake. If anybody has a short question while Wim sets up his presentation. If there are no questions, you can start, Wim.
Martha, did you have one?
I kind of do have a question. I mean, I'm thinking about what it means to spontaneously attend to relations, because I think what you're suggesting is that they're attending to the relations among the numbers, but they're not really deeply attending to the relations in the story problems when they are doing this overuse of proportional reasoning. They're thinking about the numerical relationships, but not the conceptual relationships in the story problems. And I wonder if that would align with how you think about this overuse of proportional reasoning.
Yeah, I mean, I think that's I think one of the things that is pretty thorny here and mentioned in the limitations that would be interesting to look at would be this kind of, I think that when they're doing these word problems, and especially these very stylized word problems, they're, you know, thinking on a different level than when they're thinking about sort of maybe more complex and everyday situations. And I think that that's already kind of one disconnect that's hard to really pull apart, that you know, that's so socialized, and the sort of solving of a word problem. And I think that, you know, for instance, Leuven's work and Wim's work going back a long way, that, you know, they take this surface level approach, and that's also showing up in this, you know, kind of the input research that's going on now. So that, yeah, but I don't know if I answered your question exactly, but I think that at least that's probably one reason why we're not. For instance, I expected that the number sensitive group would potentially have higher score than, because they are attending to those numerical ratios. So,
right.
But yeah.
Food for thought. Thank you.
Yeah, thank you. Good question.
Okay, sorry, I had trouble getting the right screen on. I guess you can see my slides now. Is that true? Yes, okay, sorry, 3 screens is too much. Okay, I'm going to present the last study in this symposium, and this last study is probably also the most exploratory one. It is a bit of a side project that combines lines of reasoning that were going on in our center and that we thought would be interesting to combine. We thought it was interesting, but I will later on show you that we also see some reasons why we cannot draw big conclusions from this study, but that's food for thought later on. You also saw probably that I tweaked a bit with the title. It now says inappropriate forms of reasoning instead of additive reasoning, because I will also look at other forms of inappropriate reasoning than additive reasoning. And we'll do that in 3 domains: proportionality, probability, and fractions. Now, why is that? Well, these 3 domains are among the domains that involve multiplicative reasoning. And these 3 domains are domains in which we were doing research and observing mistakes made by students, but we weren't necessarily combining them. While, of course, behind each of these domains, there is multiplicative reasoning involved. And I can easily refer here to the idea of Vanluydt to say that many situations are defined by multiplicative structures. And learning multiplicative reasoning doesn't happen in isolation in each of those areas of proportional reasoning, fractions, probability, and so on, but it happens in a relation to each other. And so we thought it might be interesting to do research to the link between these concepts. So if we look at how students reason in proportional problems, and that will be mixtures today, in probabilistic problems, which are proportional problems, but some or many say there is a specific kind of reasoning involved, and in fractions. And you can then wonder, if you look at tasks in the same students, whether students perform similarly, or if students make mistakes, whether these mistakes are the same in students across these domains. That's the essential idea of the study. So I don't have to explain much about what proportional reasoning is. People have said a lot about it. Here's a problem, and it involves finding the multiplicative relation between, in this case, silverware and pieces of china across or within the measure spaces. And the frequent mistake people make, as reported in literature, is that people do additive reasoning. For instance, reasoning that if you take 28 more pieces of silverware, you need 28 pieces of china more, or in the other measure space. Okay, so you can ask, this is then a different kind of problem. So the previous ones were missing value problems. You can see there's one value that is unknown. You can also ask comparison problems. For instance, here you can ask which paint will be darkest. It's a mixture problem, and then the ratio of dark versus white, or dark versus the total number of cans of paint will give you the answer which paint is the darkest mixture. Okay, probabilistic reasoning then could be done with very similar comparison tasks. If the bird is going to pick a berry from one of the two boxes, which box is best if he wants to pick a black berry, then he can look at the ratio between black and white, or the ratio between the black and the total number of berries here. Okay, and again, the literature reports various kinds of inappropriate reasoning that children exhibit in this kind of tasks. The first one is interesting because it basically is additive reasoning. Children may think that the box with the largest difference between black and white is the most likely box. And in some cases that's correct, but you can create items where this is incorrect, of course. But other mistakes have been reported. For instance, children will pick the box with the largest number of blackberries or the smallest number of white berries. In some cases that would lead you to the correct choice. Sometimes it wouldn't. Okay, then fraction comparison, which is again a kind of multiplicative reasoning. If you ask children which fraction is larger, of course they will have to judge the numerical value of the fraction. But again, you see a lot of mistakes being reported in the literature. A well-known one is natural number bias ideas, where students notice that the fraction with the larger number should be the larger. In this case, that's correct, but it's not necessarily correct. So you can create items where that's not correct. But interesting, gap thinking is also being reported, where children here would notice, for instance, that going from 1 to 3, 2 pieces are missing, and going from 3 to 5, 3 pieces are missing. So they would think that 1/3 is larger because there's a smaller gap between the numerator and the denominator. Other kinds of incorrect reasoning, for instance, that have been reported in literature, are children thinking that a larger denominator leads to a smaller fraction, regardless of everything else. Okay, so if we want to look across concepts, we might look at similar mistakes in students across these domains. And so in the current study, we wanted to focus on various kinds of incorrect reasoning as well as correct reasoning in primary school students in these 3 domains of fractions, proportions, and probabilities. And this told us that we needed a within subject design where children solved the 3 kinds of tasks, and that the task should be very similar, except for the fact that sometimes it would be on fractions, sometimes on proportions, and sometimes on probabilities. So we engaged about 155 students from 3rd to 6th grade who got 3 tests, each of 24 items, 24 on proportional reasoning, 24 on probabilistic, and 24 on fractional reasoning. and to show you how we matched them. So we gave them proportional reasoning tasks on mixtures to say which paint is darkest. And then you have to look at the ratio black versus white, of course. Probabilistic reasoning was with the very same items, but this time we put a context in there to say somebody is going to grab a can from a box and she's blindfolded. So what's the likelihood, or which box has a larger likelihood to draw a black can? So basically that's the same kind of reasoning that you would require here. And then circling the larger fraction is then another kind of items, but if you will see, and if you will compare the items, so here it's 4 out of 11 compared to 1 out of 4, and that's exactly the same fraction that is being shown in the probabilistic task and in the proportional reasoning task. Okay, then what we needed was a detection of the reasoning profile that the student was following, assuming that the student follows a kind of reasoning which can be correct multiplicative, or it could be additive, which is gap or difference reasoning, or focusing on where the larger numbers are, for instance, natural number bias reasoning, or in probability, the more desired outcomes. Could be other kinds of reasoning that I will not focus on today. Then we need to turn the pattern of students into a reasoning profile, because these are comparison tasks. We cannot just count the number of correct answers. We need to judge qualitatively whether a student is following a correct way of reasoning, or an additive way of reasoning, or, for instance, a natural number biased way of reasoning. And to do so, we designed an item set wherein we could distinguish that. So here you see a sample of that. That's not all items, I think, almost all, wherein you can predict if a student follows a particular kind of reasoning, whether he will get the right answer. And of course, with the correct kind of reasoning, you will always get the right answer. With an additive kind of reasoning, you can predict that certain items will be solved incorrectly. And if you focus on a larger number, other items will be solved incorrectly. And that way you can calculate the overlap with a certain theoretical profile. And that's how we assign students to a particular profile of reasoning. Okay, some results, but I will take the essentials out of it. First of all, of course, there are always students who don't follow a particular profile and they do other things that we cannot really tell what they are doing. And you see that happens, well, quite a bit, but it decreases from 3rd grade to 6th grade, and it happens in all the domains. But this isn't the really interesting group. Correct profiles, that's a more interesting group. And to our surprise, it seemed that the probability items were far easier, or solved better at least, than the other 2 kinds of tasks, and that fraction tasks were the hardest. In some cases, people will claim that fractions are precursors of proportional reasoning, and that proportional reasoning is a precursor for probabilistic reasoning, which is a particular application domain. But it seems that the opposite is the case in our findings. Students do better on probability items and worse on the fraction items. Okay, additive reasoning or gap or difference reasoning, depending on the domain, but it's basically the same error pattern, is quite rare, but you see it happening quite often in 4th grade for the proportion tasks, but not for the probability tasks, while all of a sudden it seems to happen for fraction and probability reasoning in 5th grade again. So the kind of mistake isn't happening at the same time in relation to age in the 3 domains that we're looking at. And then natural number bias reasoning, or the larger number is the larger chance, or whatever the context then is, seems to happen mostly in fraction items and mostly in younger students, which isn't really a surprise, but it is quite rare in the other domains, a bit in 3rd grade in proportion and probability, but it is overall quite rare. Now, what's more interesting, I think, is to combine here, but just show you how consistent students are across domains. The proportional reasoning versus fractional reasoning, and if you then see students who reason correctly on the proportional task make quite often mistakes on the fraction tasks, and vice versa to a lesser extent. So being in a correct profile in one task doesn't imply being correct in the other task. And the same happens for the additive reasoning. I mean, there are few students who reason additively in the fraction tasks, but they don't necessarily do so in the proportional reasoning task. On the contrary, they most often are correct. And the same goes for the natural number bias idea. So students who reason in natural number biased way on the fraction task most often do other things on the proportional reasoning task and vice versa. So quite little consistency. If you combine in other ways, probabilistic reasoning and fractional reasoning, you see basically the same things. So being correct in one doesn't imply at all that you're correct in the other. And especially if you're doing well on probabilistic reasoning, it doesn't imply at all that you're doing right on fractional reasoning. You make lots of other mistakes there, mostly natural number bias mistakes. And additive reasoning in one doesn't imply additive reasoning in the other, and so on. And the same holds if you combine proportional reasoning and probabilistic reasoning. Here you see the strongest gap. So for fractional reasoning, the consistency isn't quite high, but if you're good in proportional reasoning, it seems that probabilistic reasoning goes rather well as well. But then when you end up in the error profiles, this doesn't hold anymore. Now, some tentative conclusions, and I will tell you why they're tentative, because I will go into the limitations as well. The number of correct answers is remarkably higher in the probabilistic reasoning tasks than in the proportional reasoning task, and fractional reasoning goes quite not so well. Additive errors are rather rare, and they're somewhat more frequent in the proportional tasks, but still they're not really frequent, and they first increase and then decrease a bit with age, which is what we also see in other studies. Natural number-based errors are found, but only typically for fraction tasks, not that much for other kinds of tasks. And then in terms of consistency, well, quite simple, there isn't much consistency across tasks. So even if you see the same kinds of mistakes in the three domains, they're not necessarily made by the same students. It is happening, the consistency is happening for correct reasoning, but for the others, there is a very limited consistency. Now, why may that be the case? Well, I think there are quite some limitations to this first study, and I think we can do better in terms of the method here, because in these comparison tasks, a lot of guessing is possible. And by guessing, you have a 50% chance of being right, which hinders finding the profile of a student. And inferring the reasoning of a student from his answer profile makes it then quite hard, because it's error prone, it doesn't provide direct evidence, and the profiles have some overlap. If you reason in one way or in the other way, you show similar responses for many of the items. And then on top of that, there was a quite small number of students per age group, which makes it hard to make good statistical claims there. And that's where I wanted to end. Thanks.
Thank you very much, Wim. Then it is Matthew's turn, or if there are any short questions. We're a bit over time, so maybe a very short question. I don't think so. So Matthew, the floor is yours.
Thank you. So hopefully you can see my slides. And thanks to Elien for organising this symposium and for inviting me to a short discussion. I do enjoy doing discussions. It does force me to listen properly to talks in a way that I don't think I always do, sadly. So let's talk about the presentations that we've heard today. So we've had three, all about predictors and correlates of successful proportional reasoning. Three different predictors focused on. I'm just going to say one thing I found surprising about each of the presentations. And then I'm going to conclude by saying, actually, perhaps we don't know as much about predictors or correlates, or at least perhaps I don't know as much, because I found some of the results quite surprising. So Elien asked the extent to patterning predicts proportional reasoning in 4- and 5-year-olds. And she has two sorts of patterning tasks, these repeating tasks and the growing tasks, and two sorts of proportional reasoning tasks, the discrete and the continuous. And it's kind of an interesting design because it's got this big gap between the two, between the patterning task and the proportional reasoning measures. And I think that's kind of interesting because it perhaps renders implausible one of the things I wanted to raise. So the main finding is this interesting pattern of correlations, which is also found in the regression analysis, where the repeating patterns correlates with the proportional reasoning problems, and the growing patterns performance correlates with the continuous rather than the discrete. So we've got this interesting grid of correlations down here, and I was very surprised by this. It didn't seem obvious to me why this would be, and I sort of spent a bit of time wondering. And I guess one obvious possibility is that there's something to do with the tasks, right? So perhaps what's going on here is that the repeating patterns require you to focus on units more than the growing patterns, and that perhaps has got something fundamentally more to do with discrete reasoning than continuous reasoning. But we do have this big gap between the time points, which would suggest if that's what's going on, it's really quite there's something quite fundamental here. If that kind of tendency survives a nearly 1.5 year gap. So I wasn't sure about that. And then I also wondered whether maybe you could account for this by some kind of developmental stage kind of trajectory hypothesis. So maybe what's going on, because Elien pointed out in her data that the growing problems are harder than the repeating problems in terms of success rates, and also that the continuous problems are harder than the discrete problems. So maybe you could try and account for this by some kind of variance argument. So maybe what's going on is on the easier problems 1.5 years ago, the people who do well on that have less variance there, and they're just generally more successful. So 1.5 years later, you're going to see that less variance for them is going to not be very predictive of the easy problems, because they're going to do really well on that as well. So maybe it's the harder problems are good at explaining harder problems, and the easy problems are good at explaining easy problems due to some kind of floor and ceiling effects. So I wondered if maybe that could explain some of this relationship, but I think that would be quite easy to test, hopefully. So it shouldn't be too hard to dig into the data and see if that might be what's going on. Again, the 1.5 year gap perhaps makes that explanation less plausible than it would be if it was all collected at the same time. Okay, but I found that very surprising, and I wasn't sure I quite understood what was happening there. Let's move on to Jake. So Jake looks at this sphoring, this kind of low-level sphoring, and whether that predicts responses to proportional reasoning problems. And I'll just make a general point about this. It seems to me that the work on spontaneous focusing that's going on really is very exciting and deserves quite a bit more attention from the rest of the research community than it's getting. It seems to me there's a really impressive body of work now from all sorts of people finding really quite impressive results. And I really recommend people look at this special issue that Jake mentioned in his talk. It's got a very nice collection of articles showing what we as a field know about spontaneous focusing tendencies across a whole range of topics. So what does Jake do? Well, he measures the extent to which children focus on these quantitative relationships, and then asks whether this predicts their performance on more general proportional reasoning problems. Of course, we're all expecting the answer to be yes. This is what everyone's hoping will be happening. But actually, the answer is kind of a bit more interesting than that, it seems to me. So what does Jake find? Well, the higher SFOR, if you're a kid with high SFOR tendencies, then you're more likely to give proportional responses to these proportional reasoning problems. So the correlation between SFOR and proportional responses is 0.35. And that correlation, fascinatingly, I got Jake to do this for me, so thanks to him for calculating an extra correlation. That correlation is higher than the correlation between SFOR tendencies and correct responses. So SFOR really makes you focus on proportional reasoning, perhaps even where that's not desirable, because that correlation is quite a bit higher than the one between the one with correct responses. And of course, as you'd expect from those two correlations, the correlation with additive responses is negative. So this is really interesting, because a standard move for a discussant in a symposium like this is to say, aha, well, we need to start doing experimental studies and look at how we move from correlations to interventions. And this result suggests that actually that's interesting in this case, because maybe if we intervened to increase SFOR tendencies, that might make the issue of overgeneralization of proportionality in word problems worse. Because as we say, being high in SFOR isn't primarily correlated with correct responses, it's correlated with proportional responses. And a big concern of the community for a long, long time, a lot of WIMS work has been focused on this, is the overgeneralization of proportional strategies where they're not appropriate. So it would be, I'd be interested if Jake has data from some of the interventions he's done on this to know whether it's this overgeneralization problem is causally related to SFOR interventions. Okay, I'll move on quickly because we're short of time. So what does WIM do? Well, he compares primary school students' performance on 3 different sorts of comparison tasks. Symbolic, which I won't talk very much about, and then 2 sorts of non-symbolic tasks. One where with the question, which paint will be darker? And one where the question is, when blindfolded, who has the larger chance of grabbing a black can? This is a far-fetched scenario. I don't know why you would be blindfolded and painting. I wonder if there's some kind of curious Flemish tradition that I don't know about. I hope not. It's going to cause a horrible mess. And what's so fascinating about this is there's this big difference and consistent difference between the proportion and probability responses. And what I found very noticeable is that gap is really fairly consistent across years. And I thought quite a long time about this, because as people in the symposium will know, there is this interesting body of work on what people call the ratio processing system. So Percival Matthews has done a lot of work on this, primarily with adults, I think, but this was an important paper that came out a few years ago, which asked a very similar kind of questions to WIMS. And interestingly, the RPS people, in this paper, this is a quote from this paper, the ratio processing system is a primitive ability existing prior to instruction. So it's essentially supposed to be analogous to the ANS. And this is the kind of question that Percival asks. Participants had to look at whether the ratio of white dots to black dots was greater on the left or on the right. And you can imagine this is very similar to an adult version of WIMS tasks. You know, you could imagine asking that with this crazy blindfold scenario and grabbing a white dot. And what I wondered about this is if this ratio processing system is indeed primitive, then the non-symbolic performance gap that WIM finds consistently across age groups has to be explained simply by the understanding of the 2 sets of task instructions, because the actual task apparently is primitive and basic, and we should be able to just perceive the ratio. But what's interesting is that gap stays very consistent. So it seems very strange to me that the gap remains consistent across ages if it's just about understanding the instructions. You know, surely you would expect children to develop their understanding of those 2 instructions differently across age ranges. It seems very odd that gap is fairly consistent. So my kind of summary there is I just don't really understand what's going on there, and it would be interesting to hear what other people think. So to summarise, I've got we've heard 3 presentations. I think there's surprising, to me at least, results from all of the 3 presentations. And I'll go back to this issue about when we move from correlational to causal experimental work. You know, normally you would say, well, we want to get to understand the causality here, but it feels to me that actually the level of surprise, at least to me, suggests that perhaps actually we don't have an adequate understanding of the correlational relationships between these sorts of variables to move to causal studies, and perhaps we need to develop that understanding more before people start doing the really quite hard work of establishing causality. Or, of course, maybe I'm just very easily surprised and everyone else wasn't. So that's another possibility. And I'll stop there. Thank you.
Thank you very much, Matthew, for your interesting overview of our 3 studies. I see that it's already 6 o'clock in Belgium, so our hour is over, but I think we can still stay a few more minutes if there are any questions. If anyone has a question, you can just unmute or raise your hand, or if not, I just want to thank all speakers in the symposium and Matthew for being a discussant, and of course everybody who attended this session. Thank you very much, all of you.
Thanks, Elien, for organizing, and Matthew and them also.
Welcome.
Thank you, everyone. I just want to remind that we have the submissions for the next MCLS Open, and we are looking forward to receive your abstract.